Okay, for this one we have y double prime minus 4y prime plus 5y equals to sine of x. So let's see for this one. Once again, we gotta find first the homogeneous. So let's look for the homogeneous. That will be y double prime minus 4y prime plus 5y equals to 0. From this, we find our quadratic equation, which will be lambda squared minus 4 lambda plus 5 equals to 0. So solving this ones, we get, can we factor this one out? 1 and 5 and 1 and negative. We have 1 and 5, and yeah, I think we can solve this one out. Can we? No, we can't. Actually, we cannot this one because of the middle one. It's a negative, and then it wants to 5 gives me 1 and 5, which should add up to 6. So no, we will need to use the quadratic. So lambda it's equals to negative 4, which will make it positive 4 plus or minus square root of negative 4 squared minus 4 times 1 times 5 over 2 times 1. So solving here, we get that this is equal to 4 plus or minus square root of 16 minus 20 over 2, which is the same thing as 4 plus or minus, so that will be square root of negative 4 over 2. So we get then that it will be 4 plus or minus 2i over 2, which then this equals to lambda 1 and 2 being equals to 2 plus and minus I, making this a case number 3. And because this is a case number 3, we get that our homogeneous solution will be e to the 2x times a cosine of x plus b sine of x. So this is my homogeneous solution. Now let's solve for the non-homogeneous, and we can apply the same methods that we've done before. So my r of x for this one, it's sine of x. And because we have sine of x, we're going to check if sine of x is not present in our equations. So even though we can see it here, it's not actually quite the same, because you can see that this one is actually multiplied times exponential. So they're not the same. If we didn't have the exponential, then yes, we would have probably have them there and present in our homogeneous, but in this case, that's not what's happening. So we check. It's sine of x, the same thing as e to the 2x times cosine of x? No. It's sine of x, the same thing as e to the 2x times sine of x? Nope. So in this case, we know that we're good, so we can use, again, basic rule, and we don't need to do any modifications. So based on my table here, I can then figure out that the yp that I will use for this equation will be this one. You have sine, so I will use this. So it will be k cosine of x plus m sine of x. So I will need to find its derivatives. So then I have here that yp prime is equals to negative k sine of x plus m cosine of x. Yp double prime, I get negative k cosine of x minus m sine of x. So let's plug in into my original equation this, and you can see that my equation should be yp double prime minus 4yp prime plus 5y prime, not y prime, plus 5y equals to sine of x. So writing everything together here, we're going to have negative k cosine of x minus m sine of x minus 4 times negative k sine of x plus m cosine of x. And this is, okay, so let me just move this one real quick to the bottom so that everything fits. All right. So we have then the 4, and then the last one will be plus 5 times k cosine of x plus m sine of x equals to sine of x. So let's put everything together. So let's put everything together here, and let's simplify, and let's see what we get. So we have here we have a negative k cosine of x minus m sine of x minus 4. Well, let's just do we have two terms, so let's do the simpler way. So we have our cosines of x, and let's see what terms we have that have a cosine. So terms with a cosine we have here, which will be negative k. We have here will be negative 4m here, and then we also have plus 5k, so plus 5k, and that seems to be all the cosine terms. And then we have the sine, and then let's check the sine terms. In this one we have negative m, and this will be negative 4 times negative k will make a positive 4k, and then this one will be plus 5m equals to sine of x. So once again, let me divide it. We have two unknowns. We have the k and the m's, and we need two equations. So I will divide them by the terms that have a cosine on them. So my terms with the cosines, I already know which one they are. So it will be everything in blue. So if I combine this, it will have negative 4k minus 4m on the left. And on the right side, I don't have any cosine. So that will be equals to, oh, this should be positive. There you go. And equal to 0. So from here, I can get the equation that 4k is equals to positive 4m, which therefore then means that k is equals to m. Whatever value we get should be the same. Now let's do it for the sine of x. And here we have then only 4k minus, plus 4m, right? Because we have negative m, 5m, so it'll be like this, so plus 4m equals to, how many signs on the other side? We have a 1. There's one sign on the other side. And if we get here, we know that 4k and 4m are the same, so we can have 4k plus 4k equals to 1. So we have that 8k is equals to 1. So we get that k is equals to 1 over 8, and therefore m should also equals 1 over 8. And here we have our constants. And then we can write our solution, yp, it's equals to 1/8 cosine of x plus 1/8 sine of x. So this is our non-homogeneous solution for this problem. And now we just combine it with our homogeneous solution, and that's both of them together. Okay, so for this problem, we have y double prime plus 3y prime plus 2y equals to e to the 2x plus x plus 2. So right away, we see that we have multiple terms on R of x. So let's just focus on the homogeneous for now, and then we'll see what we need to do regarding those multiple R of x's. So once again, for the homogeneous, we have y double prime plus 3y prime plus 2y equals to 0. So characteristic equation for this one will be lambda squared plus 3 lambda plus 2 equals to 0. We can factor this one out. So we have lambda, and this will be plus and plus. We have 1 and 2. And therefore, we get here that lambda 1 is equals to -1, and lambda 2 equals to -2. So based on this, we get this is a case 1, and therefore my solution for this one, my homogeneous solution will be C1 e to the negative x plus C2 e to the negative 2x. Now, we have multiple Rx's, as we can see. So the best thing to do is to divide them. So we're gonna do one for this one, and then we can do another for this one, and another for this one. But because we see that these two are algebraic, this is a constant, and this is an algebraic term, we can basically group this one, and this one will be separate. So we'll have yp1 and yp2. So, or I guess R of x1 and R of x2. So let's do for the non-homogeneous. And once again, we have then R of x, or R, let's name it R of x, R1 of x. We're going to put the e to the 2x. And then we'll have the second R of x with the other two terms. So just thinking for this one, we're just only focusing on this one. Let's see the table. Let's see what we can get here. So for this one here, we can check then that e to the 2x is not the same thing as e to the negative x, and e to the 2x is not the same thing as e to the negative 2x. So we can use basic rule. So therefore, we have here yp1 will equal to ce to the 2x, and there's no need for the modification. So we'll find yp1 prime, which will be 2ce to the 2x, and yp1 double prime, which we're going to get 4ce to the 2x. We put this in our original equation, which is yp1 double prime plus 3yp1 prime plus 2y yp1 equals to e to the 2x. I'm only focusing on that part. After we substitute the values, we're going to get here 4ce to the 2x plus 3 times 2ce to the 2x plus 2 times ce to the 2x equals to e to the 2x. So from this one, we can combine all of the terms. We have 4 plus 3 times 2, that's 6, so that's 10, plus 2, that's 12. Ce to the 2x equals to e to the 2x. We can cancel these two terms, and we can end up with 12 c equals to 1. So from here we get then that c is equals to 1 over 12. So then we can get from here our first yp. I'm going to write over here. So yp1 is equals to 1 over 12 e to the 2x. So one of them, it's done. So it's not yet the whole problem. So now let's focus on the following yp. So I'm going to use this color now. So now we have yp2. And because we had, or I guess before that, let me write what my r2 of x is, which for this case will be x plus 2. Once again, I can do them separately, but because both of them are algebraic terms, I can basically group them together. So based on that, we can see that we're going to use basic rule because, I mean, none of those are even present in the equation that we have here at the beginning. So we have here, once again, basic rule. And then yp2 following the table, since this is the algebraic, this one, we start with the highest term, which will be an x. So because this is the x is the power of 1, we have then k1x plus k0. We always want to go all the way down to the constants. And you can see that this does even fit the terms that we have. So there was no need to do them separately. We can do them together when they're algebraic. So let's continue. So then we have yp2 prime, find the derivative, and we only get k1, yp2 double prime, and we get 0. So once again, what was our original equation? We had yp2 double prime plus 3yp2 prime plus 2yp equals to x plus 2. So putting everything together here, we are going to have 0 plus 3 times k1 plus 2 times k1x plus k0 equals to x plus 2. So solving from here, we can simplify and we can get 3k1 plus 2k1x plus 2k0 equals to x plus 2. So once again, we have two unknowns, k1 and k0, and we need two equations. I'm going to separate them. So the terms that I have with terms that have an x on them, so that will be this one. So I have 2k1, and on this other side, the only one on the left, and the other side I have 1x. So that's equal to 1. So from here I get that k1 is equal to 1/2. Then I'm going to do the terms that have a constant. So terms are constants. In this case, 3k1. And we have plus 2k0. And that equals to 2. And because I already know what k1 is, that's 3k1. So that's 3 over 2 plus 2k0 equals to 2. So when we factor this one out, we're gonna get here 2k0, it's equals to 2 minus 3/2, which then we have 2k0, it's equals to, so 2, it's 4 over 2, so that's 1/2. And to get rid of that 2, we have then that K naught will be equals to 1 over 4. So then we have that our second YP right here. So my YP2 it's equal then to 1 half X plus 1 over 4. And now my final general solution will be of the form of C1 e to the negative x plus C2 e to the negative 2x, and we have plus 1 over 12 e to the 2x plus 1 half x plus 1 fourth, and all of this, it's that solution to the whole equation. This is my general solution. So you can see we did multiple examples of these kind of problems. They're pretty straightforward. They're not difficult. So make sure that you review this for whenever you're going to have a quiz or exam. The process is the same. Next videos, we're going to cover analysis of like other mass spring damper systems, but with force oscillations. And then we'll see a different method of solving the non-homogeneous ODEs by using variational parameters. That's it for now. And as always, good luck.